Welcome back, Night Owls. This is Dr. Nighttime. Tonight we're continuing with the LTAM course. Here I'm going to present the solutions to the SOA problems that I feel relate to the second half of the content of Chapter 5. These correspond to SOA problems 5.2, 5.6, and 5.7. So, for 5.2, you're given that big A sub x is 0.3, big A sub x plus n is 0.4, and big A sub x colon angle n first is 0.35. They give you the interest rate, and you're asked to calculate little a without the dots, little a x colon angle n. So, there are three things you have to notice. First, since they're giving you insurance values and you have to calculate an annuity value, you probably need the annuity insurance equation. That's one thing. Next, take a good look at this a x colon angle n first. What does that mean? It means you get paid 1 in n years, assuming those n years happen first, that they happen before you die. There's a name for that. Pure endowment. So this a sub x colon angle n first is just NEX. That's just the endowment. Lastly, we have a without the dots. We need the equation that relates annuities immediate to annuities due. So we need to know those three things. Annuity insurance formula, definition of endowment and recognizing that this is an endowment, and the equation relating annuities due to annuities immediate. So, first thing we'll do is we'll use the annuity insurance equation to just get a double dot x and a double dot x plus n. Next, we have the definition of our pure endowment, right? So NEX is just going to be 0.35, and we know a double dot x colon angle n equals a double dot x minus NEX times a double dot x plus n, right? Standard, you can think of it as standard thing for a term annuity, you can think of it as a frank annuity, either one works. Crunch your numbers and you get 1029, but we're not done yet, because that assumes payments at the beginning of the year conditioned on surviving to the beginning of the year. Here, payments are at the end of the year conditioned on surviving to the end of the year. And as you may remember, to do that, these two are the same most years, right? Pays 1 when the calendar rolls over as long as you survive the New Year's party, minus the 1 at the very beginning, because of payments at the end of the year, so only one of those will pay at the beginning of the first year. And then add in a payment for the end of the last year. Again, conditioned on you surviving that long and accounting for interest. So it's a x colon angle n equals a double dot x colon angle n minus 1 plus NEX. Crunch your numbers, right? Remember this NEX is 0.35. Gets you 964. Alright. 5.6. For a group of 100 lives age X with independent future lifetimes, you're given each life is to be paid 1 at the beginning of each year if alive. They give you AX and squared AX. They give you the I value. And they say Y is the present value random variable of the aggregate payments. Using the normal approximation to Y, calculate the initial size of the fund needed to be 95% certain of being able to make payments for these life annuities. Okay. So, normal approximation to Y. That means we need a mean and a variance. Oh, I guess more fundamental than that. If you're looking for values of independent annuities, and you're given insurance values. Annuity insurance equation, right? You should be thinking about that. If that isn't intuitive to you yet when you need an annuity and you're given an insurance figure, or the other way around, it should be. And hopefully with a little more study, it will be. That's one of those things that if you haven't been seeing that enough, well, I guess when you get into chapter 6, you'll end up doing that calculation enough that it will be second nature to you, one would hope. So don't worry if it's not quite, I guess when I said it should be, I should have said it will be. So don't worry too much if you feel like you keep forgetting that formula. You're going to see it so much in chapter 6 that realistically there's no way that you would just forget it. It's going to be intuitive. So don't worry too much about that. Anyway, so annuity insurance formula to get anything in terms of this annuity. And for variance, we need to remember how to take variance of an annuity. And that also comes from the annuity insurance equation, right? Variance of an annuity is 1 over d squared times variance of the insurance because of the annuity insurance equation. And lastly, 95% certain, one-tailed confidence interval, critical z-value is 1.645. So those are the pieces we need. And you should be thinking about each of those. Annuity insurance, variance of an annuity, and normal approximation, mean plus 1.645 times standard deviation. And that's what we do. Right? Expectation of y is 100 times, right, because there are 100 of these. Remember, if we're adding up 100 independent things, the expectation of the independent sum is just the sum of the expectations, and the variance of an independent sum is the sum of variances. So we do 100 times the value of one annuity, that's 1155. To get the variance of this, you'll get 100 times 1 over d squared times squared ax minus ax squared. And what you're looking for is mean plus 1.645 times the standard deviation. Right? Standard deviation square root of the variance, and that gets you 1200. And last problem. You're given big A 35, big A 65, 30p35, and an interest rate. Calculate 1000 A double dot 2 35 colon angle 30 using the two-term Wohlhaus approximation. So two-term Wohlhaus approximation is where you use your Wohlhaus staircase and you only do trapezoidal approximation, right? So on this you only look at these straight diagonal lines. You don't worry about curves and derivatives. So what I recommend doing is, you might have a formula memorized that will directly relate A double dot to A double dot super 2. That's fine. In the event that by the time you're studying chapter 7 and chapter 8 and chapter 9 and such, you don't remember that particular one and you just need to draft it up again, well, Wohlhaus is a good way of approximating, relating a sum to an integral. And so you can relate these two different sums to the same integral. So you can say A bar x colon angle n. This is not formatted properly. These dots should be here. But it's approximately A double dot x colon angle n minus 1/2 1 minus NEX. But it's also equal to A double dot super 2 x colon angle n minus 1/4 1 minus NEX. Note, this denominator is always 2 times the compounding frequency. Okay, so relating these two to each other, we get A double dot super 2 x colon angle n equals A double dot x colon angle n minus 1/4, right? Yeah, minus 1/2 plus 1/4 gets minus 1/4 times 1 minus NEX. So we know 30E35 is going to be 30P35 times 1.04 to the negative 30, right? Definition of endowment and how you calculate it. We get that figure. they gave you big A35 and big A65. I wanted this to all fit on one slide, so I didn't do that explicitly, but just using the annuity insurance formula, we can get little a double dot 35 and little a double dot 65. So we crunch those numbers in. You should get 17.559. Again, calculate each of these with the annuity insurance formula. If you don't remember that, just go back to the previous problem where I walked you through it. And then lastly, you'll say little a double dot super 2, 30 colon angle 30, 35 colon angle 30 is going to be little a double dot 35 colon angle 30 minus 1/4 1 minus 30 E35. And there you go. You get 17.377. So you multiply by 1,000 and you get roughly 17,380. Alright. So as always, if you like the way I explain things and want to arrange private lessons, click the link in the description below. And until next time, this is Dr. Nighttime wishing you a good night.